Hi, my name is Amy Sullivan, and I'm the current immediate past president of AAAR. It's my pleasure to welcome you to our 42nd in our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. And so each month, the editors of AS&T select a high-impact paper to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us a chance to gather outside of the annual conference. In addition, these lectures are being recorded and will be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, all of our lectures are being hosted by one of our student chapters. And with that, I want to thank all of you for joining us, and also everyone who has helped to make these lectures happen. With that, I'll turn it over to our student chapter from the University of Miami to introduce our speaker. Thanks.
Thanks, Amy. Hello, everyone. My name is Amin Shirkhani, and I'm the president of AAAR student chapter at the University of Miami. Thanks for joining our April lecture series. It is my pleasure to introduce our speaker, Muhammad Tanvir from University of Eastern Finland. Muhammad is currently a PhD candidate in the Fine Particle and Aerosol Technology Laboratory. Today, he will present his recent work on aerosol synthesis of flame-form carbon dots. So with that, I'll hand it over to Muhammad to begin the talk. So just one quick reminder for everyone, so they can ask their question in the chat. Muhammad will get to that at the end of the talk. Thank you.
Hi, everyone, and warm welcome to all of you, and good afternoon from Finland. I'm really grateful for the whole team for giving me an opportunity to present my work at this wonderful forum. So this lecture is about aerosol synthesis of flame-form carbon dots, insights of size, morphology, and optical properties. This work is actually I published in Aerosol Science and Technology Journal in 2024. Currently, I'm associated with the Fine Particle and Aerosol Technology Lab. So I would love to briefly introduce my university and lab, so that you people can actually see who we are and what we are doing. So University of Eastern Finland is located in eastern part of Finland, and it is comprised of two campuses, one located in Joensuu and other one is Kuopio. We are actually in Kuopio campus. This university has 4 faculties, and our lab is actually coming under the Faculty of Science, Forestry and Technology. It is a mid-sized university as for Finland, with 118 major subjects, 3,500 members of staff, and around 17,600 degree students, including 1,450 international students. So there is a lot of international people in this university also. Kuopio is a 8th largest city of Finland. This is a really nice place with wonderful landscape full of forest and lakes. It provides a quite good Nordic vibes. It has around 125,000 people with 6,700 UEF students. And in 2023, Kuopio is ranked as the second most attractive city in Finland. Who we are actually Fine Particle and Aerosol Technology Laboratory. And we are actually focusing on aerosol and high temperature processes. Major focus areas are combustion aerosol group and sustainable material group. Mostly our research is based on CFT and thermochemical models, and our research areas are headed by Professor Anna Lahti, Professor Oli Supula, Professor Ijar Kutasari, and around 30 people are actually working in lab and performing different roles, as you can see here in this slide. The group emission and aerosol group is basically dealing in particle and gas emission factors of combustion process, such as power plants, small-scale combustion, engines, and wildfires. Also, they are dealing in climate emission and health effects, optical properties of combustion particles, and also health hazards, compounds, and their exposure, atmospheric transformation of emissions. Also, they are dealing in emission control strategies such as electrical filters, catalysts, carbon captures, novel combustion technologies, Last but not the least, they are also covering the area of thermal processes for resource recovery, such as some ash and side stream kind of products. Also, they developed some kind of process for the resource recovery system through combustion sites. The other side, that is sustainable material group, this is actually my group in which I'm working. And this is specialized in aerosol and high temperature process for preparation of sustainable materials that can be used for the green technologies. We are actually producing material for battery material for the battery material production and carbon capture and utilization, and then photocatalysis and gas sensing applications. In our lab, we have a different high temperature process for the synthesis of material, like flame spray pyrolysis is there, and also we have high temperature induction annealing systems, high temperature furnaces. Also, we have spray pyrolysis and many other different synthesis routes. And we are actually producing different kind of materials like metal oxide, metal composites, carbon nanostructures, carbon nano onions, carbon darts, graphene, and all carbon-related particles. So we are open for the collaboration in these areas. Yeah, thank you. This work is basically based on my article that was actually published in 2024 related to aerosol synthesis of flame-formed carbon darts. And in this article, actually, I provide some insights about the size, morphology, and optical properties. And in this article, I have established gas to particle formation mechanism based relation for the structure to property relationship. Like in this article, I have studied composition of carbon darts, size, morphology, and its structure, and how these properties can affect the optical features. As we know that carbon darts have been studied and produced through different aerosol processes, but as for my understanding, it has not been yet discovered by flame spray pyrolysis. So this study can be you can say a way forward for the mass production and one-step synthesis of carbon darts. In this method, we have used two kinds of configuration for the flame spray pyrolysis: open flame spray pyrolysis and closed flame spray pyrolysis. And using these techniques, we have explored the mechanism of particle formation, and then using that mechanism, we have established a structure to property relationship that actually can give us an idea how the particles features can contribute to the optical properties of the carbon darts. So what are carbon darts? Why we are so much talking about this particular nanostructures? These are basically very fine particles around 10 nanometer in size. Predominantly, they are amorphous, and they also have some crystalline cores that can actually induce some particular features in these nanostructures for the photoluminescence and optical features. Also, they are mostly sp2 hybridized with some sp3 factors. It depends upon the synthesis routes, like from where you are actually trying to produce it. Either you are using bottom-up or top-down approach, so it can actually tune up the requirement of sp2 or sp3 structure in your carbon dart, and according to your application. Also, they are highly dispersible in water. They are hydrophilic in nature, so they can be used in water-related applications. They are less toxic compared to metal-based quantum darts like zinc darts. So they can be used in some biological applications like biological sensing. They have numerous functional group on their surface, so they are highly reactive and can be used in a reactive atmosphere. Last but not the least, they exhibit excellent photoluminescence and optical properties. Like you can see, they exhibit photoluminescence and absorption in UV and visible region. So depending upon their photoluminescence behavior, they can be used in different applications as per requirement of the application. So let's talk about some of its applications. so that we can understand the importance of carbon dots. So these carbon dots are mostly used in photocatalysis. They can be used as a sole photocatalyst, or they can be doped with metal oxide to tune up their band gaps. For example, titanium it is widely used as a photocatalyst, but the problem is it is mostly active in UV region. So to tune this titanium to enable it to visible driven, we can dope it with the carbon dots that can actually narrow its band gap and enable it to active in a visible region. So it can be used in then visible driven applications. Also, it can actually control the electron hole recombination process, so it can increase its photocatalytic activity. It can tune up the surface and act as a photosensitizer. So it has numerous areas that can actually improve the photocatalysis applications. Also, it is used in biological sensing applications, owing to its photoluminescence enhancing and quenching features. It can actually sense the tumors or infection inside the living bodies. Also, they are used in fuel cells as a functioning layer to improve the power conversion efficiency. Also, in case of supercapacitors, they are used as a hybrid electrodes, and in this way, they can bridge the gap between high power and high energy density. Also, they are using as a gas sensing element because they have a very high surface area, have a defects induced structure, and they are electrically conductive. So they can detect air pollutant and also industrial gas emissions. In our recent article, we have established a carbon nano-onions through the same flame spray process method, and we have used it for the hydrogen sulfide detection. And it can actually sense this H2S gas at room temperature. So it is workable in real-time applications. So this article is under review and it will be open for the author soon. And then what are the conventional synthesis routes for the carbon dots? They are produced through bottom-up or top-down approach. In bottom-up approach, we have options like chemical oxidation, microwave assisted methods, hydrothermal treatment system, and ultrasonic treatment. And in case of top-down, we have laser ablation, plasma treatment, acid refluxing, and electrochemical oxidation systems. If we compare these two systems, then we can we can distinguish them on the basis of their principle. Like top-down can be basically fragmentation of bulk carbon material into nanoparticle. But in case of bottom-up, we are actually going from the nucleation to the particle stages, like chemical assembly or carbonization of small organic molecules that can be enabled to form a large particle. As far as quantum yield is concerned, top-down synthesis routes can provide a very low quantum yield, but in bottom-up, we can have a quite high quantum yield. And structural control can be obtained like bottom-up, top-down can control the carbon core and crystallinity, and bottom-up can tune the functionalization and doping features. So depending on the application, so we can select different routes and then we can produce material and tune up their properties. So there are many options to play with the synthesis routes to establish a particular kind of carbon dots. Also, for scalability point of view, top-down approach is not so effective because it required quite high energy, and there is also need quite sophisticated equipment, so it's very costly. But on the other hand, bottom-up is quite good. It can be used for the mass production and eco-friendly environment. Also, top-down is quite expensive. It's quite time-consuming. Harsh conditions are required. But in case of bottom-up, It's typically low cost, fast, and utilize some small laboratory setups. Flame-based methods lie under the category of bottom-up synthesis routes. And in this technique, basically, we control the combustion condition. We introduce a few rich conditions in our system and then control the atmosphere and produce the carbon darts or carbon nanostructures according to our need. As far the earlier studies are concerned, carbon darts are produced through the soot derived from the candle. In these strategies, soot are treated with the acid oxidation systems, and their different particle ranges are then segregated. And after that, also their functional materials, surface functional properties are also tuned up. This enable the material to tune up its photoluminescence features in different regions of the UV visible spectrum. As you can see in this diagram, different sizes of the carbon darts have been segregated and then they are used in different regions. So there is a lot of option here to use candle soot also. The other option is from candle soot point of view, it can be doped with nitrogen or some other heteroatoms so that properties of the carbon darts can be changed, and then their application can be tuned up accordingly. So in this system, in this study, they have actually doped carbon darts with nitrogen and modify its surface chemistry and then used it as a detection material for the water treatment systems. Like they can detect heavy metals like mercury and iron. So it has application in these areas. The other option for the flame synthesis routes can be mechanoburner. This is really a good system. It has provided quite good insights for the production of carbon darts through flame routes. So here you can see the setup of mechanoburner. They have used high sooting flame and low sooting flame, and then collected the particles on the glass plate, and then these collected particles are then post-treated through different solvents. Like they have used dichloromethane to extract the small particles, like small, very fine nanoparticles, and then they have used NMP for the larger particles. So depending upon their particle size, they exhibit different kind of optical features. These NMP for dichloromethane derived carbon darts exhibit UV light fluorescence, so they are blue darts. And these NMP derived carbon darts exhibit photoluminescence in green region, like in the visible region, so they are considered as a green dots. So this can be an option. And then using the same setup, the mechanoburner, they have studied how the combustion condition can be changed to tune up the properties of carbon darts. So here you can see they have used equivalence ratio as a tuning parameter. So they have used different equivalence ratios, and according to this change, they observed a band gap change in their nanostructures. So when they increase the equivalence ratio, so it will actually increase the particle size of the carbon darts. So particle size increment mean that they are now shifting from blue to the yellow dot region, blue to green, and then yellow dot region. Then it just means that they can be active in the UV region, UV visible region, and high visible region. So this is also an option, like by tuning the combustion condition, we can produce our material as per our need. And then they have studied the origin of photoluminescence, so why it is happening in these nanostructures. They have observed that the blue dots are basically small PHS, like polyaromatic hydrocarbons, trapped inside the particles. which are active by UV light because they are quite small and they have very large band gap. So they need quite high energy to be active. So they are considered as a UV blue dots. And these yellow green dots are basically large fragments of polyaromatic hydrocarbons, because these polyaromatic hydrocarbons fuse together, conjugate together, and form the large clusters. So as the sizes of these nanostructures increases, their band gap will decrease, so that they can be band gap will actually increase. So they can be active than visible light. So they exhibit fluorescence in a green region. And then these yellow dots are basically due to some size related features, defects, and also some functional groups, some chrome 4s on the surface of carbon dots, which also contribute to the photoluminescence features of carbon dots. In the next study, they have studied and they have shown that temperature is also contributing a quite prominent role in the quantum yield and also in the fluorescence of carbon dots. As they increase the temperature, like you can see here, the quantum yield and the fluorescence will increase. And they also shown that the homolomo gap, I mean the band gap, you can say, for the molecules, is affected by the different functional group and also the polyaromatic hydrocarbons. So as the sizes of these PHS increases, or the nature of functional group on the surface of carbon dot is changed, the homolomo gap will change, and it will actually give a different kind of photoluminescence. So by tuning these parameters, application of carbon dots can be changed and they can be applied in different areas. Also, the pi transition and some chromophores on the surface of carbon dots plays in defining the optical features of these nanostructures. Although these flame sensor routes are quite effective, but still there are some limitations, and there's still gap to fill. Like these systems need a post-treatment steps, which increase the cost and also time. They are difficult to handle multi-component precursor feeding. So if there is a multi-component reaction system, then it's difficult to control it. Like we cannot use this system to dope our CDs to further tuning the properties of these nanostructures. Also, their burn stability is quite sensitive, and under higher loading, the flame can be extinguished. And then particle collection for large production scale rate is challenging. So there is a big big need for the gas phase sensors that can be used without any extra post-treatment steps, and that can provide a continuous and mass production. In this respect, Leo has proposed a DFT model and suggested that through pre-mixed flame systems, we can produce some flame-form carbon nanostructures which can exhibit carbon quantum behavior. So he has proposed that we need to actually control the combustion condition so that we can control the size of the particles, and also we can induce some organic compound in like composition of the carbon dots, like the PHS basically. So we can, if we can control them, then we can control its band gap, and also there is a need certain kind of graphitization, so that we can induce some structural defects also. So these composition and graphitization of carbon dots can actually tune up the properties of these nanostructures and enable them to be quantum to show quantum behavior. But the problem is what can be the system? This is a good solution way forward for the one-step and scalable sensors of CDs. But still, there's a question like how actually we can do this. So in this regard, flames pyrolysis can be a really good option, because it's a facile one-step synthesis route for gas to particle formation, and it's a combustion drive system. So it can handle also multi-component systems. So if we want to produce some doping or composite in our carbon nanostructures, then it is also possible through this wonderful system. And it has been widely studied for the metal oxide and composite materials. And even it has been used by Evonik, Cobalt, DuPont, Crystal, and Ishara Industries for the large facilities to produce carbon black and metal oxide. So currently there is a limited understanding of flame synthesized carbon dots via FSP. So especially the structure property relationship is really vague and need to further studies. So this study actually provide fill up this gap and provide a gas to particle formation driven structure property relationship and provides an insight about its size evolution, morphology, and structure. So this can actually provide a way forward for the one-step and scalable synthesis of carbon dots. Yeah. So how actually this flame spray pyrolysis is working? So we have two options, like we can use an open system and a closed system. So this is an open system for the flame spray pyrolysis. In this system, precursor is injected with the help of some parasitic pump into the reactor, and then by using a dispersion medium that is quite high pressure gas, this solution of precursor is converts into micro droplets. And when these micro droplets are exposed to flamelet, because this precursor is quite highly flammable, it starts to ignite and transform into undergo some reactions, because we have oxygen here using this entrainment air and also from the dispersion air. So due to this oxygen and high reactive atmosphere like temperature is there, so this starts to produce different gas phase products. So when the gas phase products concentration is quite high, they are saturated, supersaturated due to high pressure, due to low pressure region, and this starts to form some nuclei of nanoparticles like carbon dots or some metal oxide, whatever we are producing. And after that, these nuclei undergo homogeneous nucleation and heterogeneous nucleation, and particle size will grow further due to these condensation and nucleation stages. Following this, downstream of flame, temperature will decrease, and also due to this entrainment of air, temperature will be quite low for the flame in the downstream. So these nanoparticle will agglomerated and transform into aggregated structures. So in the next setup that we have used here for the carbon dots is basically closed system. Here we have introduced a quartz tube that can entrap the flame. So when we ignite our precursor, then we have very limited, oxygen from the surrounding, because we have entrapped this flame inside the quartz tube now. So due to this oxygen deficient environment, so now we have an opportunity to control the combustion conditions here. So this will enable us to produce and tune the carbon nanostructures, carbon dots here. And also, due to this quartz tube, the flame is quite hard compared to open system. So we can actually induce in situ graphitization of our material. So it has a numerous advantage here. So to understand the mechanism, what is actually happening inside the FSP, so here you can see different stages of the particle, how actually it is growing inside the flame. And from this point of view, this region is very important. So these blue dots are basically precursor solution that is in the micro droplets form. When it exposed to this high temperature, this red line is basically temperature line. So temperature will when it will be exposed to this high temperature atmosphere in the flame, the gas phase products will start to form. Exponentially, they will start to form, and then there will be a point where they are super saturated, and at that point, nuclei of carbon nanostructure will start to form, and this orange line is basically indication of formation of nuclei of carbon nanostructures. So here basically, or the whole system operates like this. Further downstream the flame, when flame temperature will decrease due to some entrainment of air, or also due to less availability of precursor over there, what happens? The particle will start to grow, and its primary particle size will grow up to certain nanometer size. And then after that, when the flame is quite cold, and particles are exposed to the room temperature, they starts to aggregate and agglomerate. So this orange line is basically show the different particle size evolution stages of the carbon nanostructures. So here actually we can see how the mechanism of particle nanostructures is actually happening in the closed flame pyrolysis. So when xylene, because we have used xylene precursor here for the precursor for the synthesis of carbon nanocarbon dots. So when this xylene precursor is exposed to high temperature and oxygen deficient environment, they produce the carbon fragments in the long chain or straight chain form. And in the following stage, these carbon fragments will start to fuse together and form the PHS rings, polyaromatic hydrocarbons rings. They act as a precursor for the series. And downstream the flame, these PHS will start to fuse and conjugate together and form the larger cluster of PHS. And then these cluster will starts to undergo homogeneous and heterogeneous nucleation, but because at this stage supersaturation condition is achieved and particles start to grow here, and following this stage particle evolution will start, and we can experience some nanometer size particles. And then when these carbon nanostructures will exposed to low temperature region or room temperature, they starts to aggregate and agglomerate. So this is the whole mechanism how particle are growing inside the this closed flame process. So in this case, actually these two stages are really important because these are actually defining the particle size and its properties. Although these small nanostructures are aggregated and agglomerated, but still they preserve its features and exhibit the features of carbon dots. So then we studied the agglomeration of our carbon nanostructures by using a scanning mobility particle sizer SMPS. So for this, actually, we have used open system, as I mentioned earlier, and closed system. For the closed system, we have used different equivalence ratios to tune up the combustion condition. Equivalence ratio is basically actual fuel to air ratio to the schematic fuel to air ratio. So this will actually define the oxygen deficient environment in the system. So that we can actually produce the carbon structure over there, and by raising the EQR, equivalence ratio value, we can change the particle size and its morphology. So here you can see for the open system, carbon nanostructures are formed on the outer edges of the flame, and their particle number concentration is very small. As you can see, it's only 19.7 times power 6 something particles, and so their collision efficiency is also quite small, and resultantly we have a very small mass particle size distribution. You can see here this black curve is basically for the open system. In case of closed system, as we increase the equivalence ratio, the yield of carbon dots is increases. Below 2 eqr, yield is quite small, so it is not quite effective. When we increase it up to 2.5, we can have a quite appreciable amount of carbon dots and with the required morphology and flame stability. But further raise can increase the yield, but in that case we can compromise the morphology, so particle will not exhibit the required feature. So in our case, 2.5 EQR is quite effective to have certain features in our system. Next, we established the primary particle size and morphology of the carbon dots through time analysis. As you can see, for open system, because of having a quite small number of particles over there, and also due to rapid pinching of the flame, we experienced small particle number size here, around 9.8 nanometer with mean value. And due to fast pinching of the flame, particle did not show quite good morphology. They are act as a loose agglomerates and with some defect-induced structures. But in case of closed system, although particle size is a little bit higher, like 11.6, due to that high temperature resistance time in the flame, because when we close the flame, then the flame temperature will be quite higher, and under high temperature, particle will grow further. So that high temperature environment can actually increase the particle size of the carbon nanostructure. So that's why we get a little bit higher size here. But at the other end, the morphology is quite good. It's compact agglomerates with some turbostatic structure. Also, we have observed stacking in our time diffraction analysis. So you can see here a ring structure with some bright dots. So this ring structure is basically carbon dots, and these bright dots are basically the graphitic carbon on the surface of the carbon dots. Also, we can see that the interlayer spacing is quite large in case of this particle. This shows that there is a quite interplay between the defects induced structure and graphitic structure. So it shows a transformation of these structure in the particle. As far as composition is concerned, we have performed some qualitative analysis to understand the composition of our particle. So this shows that like this blue circle can show the region where we get quite high peak. This shows elemental carbon. Overall, carbon dots are composed of organic carbon and elemental carbon. So these structures basically define the overall composition of the carbon dots, and then tune up the properties of these carbon nanostructures. So you can see here for the open system, organic carbon to elemental carbon ratio is quite high, but in case of higher like EQR value, this can be quite lower. This shows that we have a higher amount of elemental carbon in our closed system. So because these elemental carbon is basically a thermally more stable and graphitized form of carbon, so this shows that our nanostructure produced through closed flames pyrolysis are more graphitic in nature. Yeah, and this can be also seen from this this finding that temperature can increase the graphitization of the sample by increasing the EC value. And then, as far as the structure is concerned, we have observed it's two distributed peak around 1350, like in Raman analysis. So we have performed Raman analysis to check the structural morphology of carbon dots, and we have observed two peaks. One peak is around 1350, that is a defect peak, and the other peak is around 1600, and this is actually graphitic peak. The peaks were overlapping, so we have deconvoluted them and them to 4 peaks, And this D4 peak is the extension of D1 peak, and D3 peak is basically the extension of G peak. So this shows that this is the part of G, as it shows the graphitic structure on the surface of PHS. Also, we have also observed the Raman analysis for our sample that we produce through closed frame sweep process. So here you can see like intensity ratio between ID and G peak is quite high for the open system compared to closed system. This shows that this open system is more defect induced in nature compared to this closed system. This is because of the composition of these carbon nanostructures. Because in open system we have more OCs. OCs are actually defect-induced structures. So this will increase the defect in the structure, and ultimately higher ID to IG ratio will be observed in case of open system. In case of closed system, we have observed a little shift from the normal peak of G. Like normally, this G peak is appearing around 1580, but in our case, it is around 1600. This shows that the interplay of OC and EC fragments. So that's why actually it is shifting from its normal position to the 1600. Next, UV visible absorption. So our sample shows different optical regions, like intense blue region, and then UV and then visible region. So intense blue region is basically due to pi-pi transition, and this is basically happening due to high energy absorption and then shifting of electron from pi to pi steric region, and this will show this kind of absorption. And in the visible region, we have observed different PHS in our sample. So these PHS actually contribute to the absorption in this region. So these studies also confirm the presence of these PHS, and polyaromatic hydrocarbons can contribute to the absorption in the visible region. It is considered that the size of carbon dots is the major key factor in controlling the optical features. But here we have seen that composition and functional group on the surface of carbon dots, they are also very important in defining the optical features of nanostructures. So as far as band gap is concerned, optical band gap is concerned, the OC fractions, these exhibit different band gaps, like because these nanostructures are composed of different fractions of OCs. So depending upon their nature of OC fraction, they will absorb different light, and then they will exhibit different band gap. So variation of band gap is basically due to the specific structural stacking interactions of these polyaromatic hydrocarbons. So you can see here how the band gap is changing according to the OC ratios. And then these like PHS, the evolution of these PHS can actually change the band gap, or you can say homologon gap of these nanostructures. So as we increase the size of PHS, the band gap will increase. So this is what we observe in our case. So for lower PHS, we have a quite high band gap, but as the size of these PHS increases, the band gap is shifted from 3 to its lower region, from 1.75 to 1.84 for these for these particles. For ECs, like ECs, actually they exhibit a different kind of optical absorption. So their band gap will be also different compared to the OCs, because these are quite graphitic in nature. So pi-pi transition will basically contribute to their absorption. So this band gap is basically due to EC2 to EC3 fractions. But we have seen that in our system we have quite higher amount of EC4 to EC6, which are basically graphitic form of carbon. So this shows that in our system the carbon dots have different kind of composition of ECs. So EC2 to EC3 will contribute to the optical band gap shifting from 682 to around 700. And then these EC4 to EC5 structures will contribute to the structural modification and then contributing to the tuning the parameter related to morphology. So depending upon these composition, we can use these EC-rich carbon darts for the application, like in photosensitizers and in different photocatalysis kind of application. So let's move to the conclusion part. This study basically give a pathway for the one-step synthesis of carbon darts through flame pyrolysis and drive the structure to property relationship for the synthesis of these nanostructures. In case of open system, we have a comparatively narrow band gap, particle size compared to closed system. And in closed system, we have more graphitic particles compared to open system. And also, as far as the composition is concerned, the EC4 to EC6 to EC1 to EC3 fraction is quite higher in case of a closed system. So this shows that we have more graphitic carbon in closed system. So here we actually can actually use our graphitic and organic carbon to tuning the properties of our carbon nanostructures. Also, OC and EC, these both features will contribute to the optical features of these carbon nanostructures. And band gap for OCs is basically lies between 4.56 to 1.75 for the closed system and 4.58 electron volt to 1.84 electron volt for the closed system, for the open system. But the EC shows quite a similar band gap for the both system because this is related to EC2 to EC3. That is quite that shows quite narrow band gap around 1.56. Also, we have studied in our recent article carbon nanostructures through these xylene precursors. So this is basically carbon core to OC core to OC shell structure we have found here. And this is quite good material for the gas sensing application. Actually, this is the material that we have used for the hydrogen sulfide detection. So this is our new study. And also we have doped these carbon nanostructure with titania. So we have observed that if we doped titania in the carbon nanostructures, then we have seen that particles are more defect induced, and also their morphology is quite, you can say, defect oriented compared to the graphitic one. So this is all from my side. Thank you for the listening, and I'm open for any questions. Thank you.
So thank you for your talk. Now the floor is open for any questions.
Sorry, can I ask a question?
Yeah.
Thanks for your presentation. Maybe I was confused because I joined a little bit late into the presentation, but I thought the usefulness of quantum dots are in their existence as individual particles less than 20 nanometers or so to be able to show those kind of special optical properties. Whereas the particles that you showed, they are already agglomerated. And so are you referring to the carbon quantum dot as the entire agglomerate, or are you referring to the primary particles in those agglomerates? And how do you think, that changes the optical properties?
Yeah. So this is quite a nice question. So as I mentioned that agglomeration and aggregation is quite common in flame spray pyrolysis. It happens all the time. But we are actually talking about the primary particle size. So although these particles are agglomerated, but still they can actually maintain their intrinsic features. So we can see these effects in the structure. As I mentioned that it's not about the size only. It's also about the composition of the particle. Like OC/C ratio is also defining the optical features. That is the major part of my presentation, and also some structural defects. These are also taking part in the optical features of these nanostructures. So it's not only size, but also composition and surface and its defects. These will also contribute in these features. But the question is quite good. Like it's good to if we collect particle from very close to the like evolution of stages, like in case where the homogeneous nucleation or heterogeneous nucleation is happening. So in our current study, we have done this. We have actually collected quite small particle around 2 nanometer, very small particles. We're able to quench those particles from very close to the flame. So the thing is, if you want to maintain the particle size quite low, then you have to collect them from the very early stages of their growth. So for that, you need to establish a special kind of you can say collecting system that can quench particle from that particular region, and then you will see the effects of those particles. But we have done this, and it is doable through FSP because this study is done in 2024, and we have now updated our system. And currently, we have achieved that level that we can now collect particle around 2 nanometer. They can show photoluminescence. They can show graphitic core also. That is missing in here in this work. Thank you.
Okay, thank you. Just a quick follow-on question, maybe on what you
Yeah,
explained.
yeah,
So the results you showed, how is that different from the typical soot aggregates that we see from any combustion process? Then, if any soot aggregate or soot agglomerate can act as a carbon dot, why don't we actually use that? Just a normal burner or a normal engine, to produce the carbon dots.
Yeah. So this is also quite effective. Like in those systems, actually, like if I compare with the flame spray pyrolysis, in flame spray pyrolysis, we have a quite good opportunity to tune up the parameters. If I go in the previous slides, I can show you the diagram also, but it's quite difficult here now. The flame spray pyrolysis system will use actually dispersion gas as you can say, oxygen medium. So we can control oxygen through that particular region and control the combustion condition in our system. As you have seen in the mechanical burner also, they have tuned up the combustion conditions over there. By controlling the equivalence ratio, they can tune up the band gap of the particles. So this is all about the controlling of the parameters. If you are using a simple sooting condition, then in that case, controlling is not so effective. But it is possible to do it if you can control the parameters over there. This is the reason, like in flame spray pyrolysis, we have opportunity to play with the different parameters to adjust the combustion condition to maintain the particular particle size and features in our system, so that we can have a particular kind of particle in our you can say system. But for the normal systems, it is quite difficult. Yeah.
Okay, thank you.
Yeah, thank you. Thank you for the nice question. Yeah.
We have 2 more questions from the chat. So the first one is, do you think ultrasonication will be able to break the weak aggregates produced in the closed system? Thank you for the presentation.
Somehow we have tried this one, like in this study, I have tried to break them, but still there are 2 actually options. If these are aggregates and agglomerates. If they are agglomerates, these are basically loosely attached particles. So it is somehow possible to break these nanostructures through ultrasonication. But if there is a aggregation like necking happening over there, and particles are surface is quite, you can say, chemically attached with each other, and then it's difficult to break them. Yeah.
So the second one is, what is next for you in exploring the materials space? Other fuels, metal combinations?
Yeah, actually, we are working in that, and as I mentioned that we have established very small nanoparticles, and we are actually looking forward to, because I mentioned that in the previous system there is a problem to control the multi-component precursor system, because we are interested in doping and composite formation. So now I'm looking forward for the you can say some doping and composite formation through these carbon darts, so that I can produce particle uh, from the flame. Not actually we collect particle from the flame and then we dope them. So I will use a multi-component system, multi-component precursor, and then use in the flame to produce some doping and composite kind of particle. Yeah. So the thing is, I want to produce a one-step system for the doping and composite material for the carbon darts, because these are quite a big requirement for the photocatalysis and gas sensing application. In the current system, we produce a metal oxide, and then we produce these carbon darts in different system, and then we combine them. So this is quite lengthy and time-consuming and costly process. So I am trying to bridge this gap and to produce a particle in situ situation. Yeah. So this is my next goal.